So, hello. We're in the second part of Section 3, Week 1. The video's up. It was on the actor script, actor manager, health, damageable, and um, picking apart the compass was starting to, which really had like three other scripts associated with it. Um, so, within here on the player, last week I had reviewed actor and actor manager or actors manager, and then damageable and health, which are also on the enemies, actors on the enemy as well. And this is the actor script, actors manager, damageable, and the health script. And all the details of that was on the previous video. And then I started to cover these three scripts with the compass. We ran out of time. So let me focus my efforts on that. So as you see here, I just kind of threw the prefab up here, and I just wanted to see what was happening, what it was looking like. So this is kind of how the enemies are being tracked across the compass. I didn't look at these directional things, so I'll look at that, I guess, after the enemies. But what's happening here is when we look at how an enemy is being displayed on the compass, we have three things we have to look at, really. So we have, if you notice here real quick, there is the actor and the health. And remember, damageable is like underneath. It's like in a game object down here, underneath where the hit target is or something. No, the hitbox space. Yeah. So anyway, all the enemies have this compass element, okay? And if you notice, the compass element has a reference to a compass marker enemy, a prefab. If I click on it, it'll pop down into the project and be like here under prefabs and UI. Here's the compass marker enemy, but you notice that there's also objectives and directions. But here's the enemy. And it is a full prefab. Actually, just all I did was go up underneath the compass here, and I just threw it up here just to see what it looked like. It's a UI element, so it has a rect transform. It has this compass marker script, which is the main script we'll be looking at, and an image. That's how we get an image up, and canvas group. I guess it's just like there's like grouping elements in the UI canvases. Like sometimes it's usually learned for like alignments, like vertical and horizontally align elements together. But this seems to be part of a canvas group, which maybe it's defined. Yeah, it's like defined when level up under compass. In either case, that's everything. And so that's what this red little dot is. And I was just kind of like moving it around just to see how this would work with when it's tracking an enemy. And then the third part of it is under the main HUD compass. There is a compass script. And just notice that it is an image. Okay, it's probably compass background. Yeah, so there's compass background, and there's like this little line. Notice that they're like their rect transform is just defaulted out. It's really like the width and height of this graphic is up here, and this is actually going to get pulled into, and we're going to figure out where to like place dots along it. So just note that the width and height here is important because that's like the full size of the rectangle that we have to play with. And so let's pull back to an enemy. Any enemy, doesn't matter. They're all set up the same. So we have compass element, right? And notice that text direction is empty. So if I didn't notice it, let me just click play real quick. Let's see, like there must be like compass bearings. I didn't notice like north, south, west, and east or something. Okay, so we get these little ticks, and we have north. Okay. So those are kind of like always showing, and they're like pre-built. They're here under directions. So we have north, northeast, which doesn't have a, it's just a tick. There's no like letter above it. Cool. I'll look at the directions later. I actually didn't look up how they're functioning. Probably has something to do with these positions I'm seeing here. But in either case, let's go back to where we really wanted to go to, and on the enemy, we have compass element here, and let's jump into that. All right, compass element. So here's its public properties. This is like, hey, what's this compass marker prefab? This is a little weird. It's not referencing the game object. So it's like a little quick. It's like saying, hey, there's some script component of type like compass marker, and I'm just gonna like reference that, but it's part of like a larger game object that we're gonna instantiate or prefab. And then text direction, which is empty. It's not text, and private is a field. What's the compass? So on awake. Go out and find me the compass. So that is up here, this thing. So it goes out and finds that. And then it says, okay, instantiate. So this instantiates game objects. And it says compass marker prefab, which is this. But it's actually, the reference link is to here. So you just have to be a little careful. And when you're saying instantiate this thing, Unity recognizes, oh, it's part of this larger prefab, so the whole prefab needs to be instantiated as a game object. So this is actually a game object variable called marker instance. Sorry, it's not a game object. So this is where it's a little confusing. So you instantiate the game object, but you reference the strip. It's like a quick way of saying, hey, instantiate this game object, but I don't want like the reference to the game object, because then I got to go down, say get component, and go find me like the compass marker component. So this is like a little quick hint of saying, yes, I'm going to instantiate this prefab, but I'm actually just pointing to that script component. So it's that compass marker script component. So when it gets instantiated, it looks like this, but our reference is pointing here. All right. So whatever, it saved them like a few lines of code. Now we instantiate this prefab, and we're pointing at the script component on it, and then on that script component on it, we're saying, hey, call the initialize method, pass in a reference to this script object, this compass element that's sitting on whatever enemy, and pass in the text direction, which is empty. All right, so if we look at this prefab that just got instantiated, we have the compass marker script here, and that's what's being called, and initialize, it's public, right? So coming in, boom, whoever the compass element component is that called me comes in here, which is from either the torrent or the hoverbot, and the string. So when this gets created, first it checks, is this a direction, and is there some text associated with it, which is not. So if you look at here, is direction, it's false by default. So this won't run, and this will run. So what's happening here? Okay, this is saying whatever compass element we just passed in, which happens to be at top of some type of enemy game object, grab its transform, and then get component enemy controller. So I'm guessing since this is pointing toward a script component, so let's just say it was enemy torrent that in this situation initiated it on its awake. Right here. It's like saying, go out and get me the enemy controller. but I guess you can't go from component to component. You either have to go up into the transform or up into the game object first, and then say go find me a component. In which case, it's going to find the enemy controller, which we haven't covered yet, but that's okay because all it's getting from the enemy component controller is just saying, "Hey, I want to subscribe to some of your events." So in the enemy controller, there is some properties that are defined, some Unity actions, which are just events. You can subscribe to them and get a method called if this event gets executed, gets actually raised, happens. And so this is like saying I want to listen to this enemy's on detected target and on lost target. And if you just look at what, and it's saying, okay, these are my methods, I want to subscribe to these events. All it's doing, it's changing the color. And then if you notice here, all the way at the end, it just says run lost target, which means just set your main color to the default color. And then if the enemy ever sees you, it changes the color on the radar. So it's like it shows you when the enemies are alerted to you, basically. So if I click on compass, the default color is orange, like hazard, be wary, and alt color is red, like imminent danger is coming in. So I was just listening to those events, which we don't need to know any more about them. We'll go through the enemy controller later. Yeah, so that is everything. I'm just interested, can one component call get component quit like that? Like, do we have to call it go up into the transform to call it? I'm just curious. Not usually I go up to the game object and call it because it's really a game object method, but the transform is like a required component and so like crazy super important and tied to the idea of a game object that the transform also kind of has access to like game object level stuff as well. But for a little experiment, I didn't really feel like having a big compile situation. It's not really worth it. But okay, looks like it's almost done. Maybe the false still running. Let me see if there's something else I can do. No, it's done. All right, let me just turn off that. I just want to see if the enemies are still connecting up and can register with the compass. Yeah, they do. All right. So they look red to me right now. Let me get one of them to alert. Yeah. So it fully turns red. So let me turn this back on. So enemy default color, or maybe the orange looked kind of red to me. Oh yeah, see, to me it looks like there's like a little. It looks orange on the outline and red in the middle. Or maybe that's just like my eyes are bad. Yeah, there's definitely like a red center. Let's see. So big white circle is the source texture. And it definitely shouldn't be a raycast target. It's not interactable. But adding. Oh, Alpha 7. No, interesting. Yeah, I just wanted to see why. To me, it looks like it's like red in the center and orange on the outside with even like another ring of red. Just looks weird to me because it should just be like a solid color. Oh no, I can see it really. There must be something else under it. Yeah, there's a foreground image. There you go. All right. So there's two images overlaying each other. Fine. So when an enemy is neutral, they still kind of want it to feel like it's an orange ring with a red center. But you can tweak that if you wanted to. All right. I just thought my eyes were going. Anyway, and yeah, I was able to just say compass element dot get component. So even at one component, you could go and look throughout the game object to find anything else. But the point is, it just wanted to get the enemy controller just to subscribe to those two events so that we can change the color based on whether they see you or not. Okay, so after this is all done, we reach the end of this method call, right? Boom. So what happens is we run all those lines of code after this initialize happened, and then we're done here. So we return back to here, and then we continue on. And now what happens is we call the compass script, and we call register compass element, and we throw in the transform of this. Now we have to be a little careful here because this is compass element, which is sitting on an enemy game object. So we're actually passing in the transform component of the enemy. And then we're passing in this marker instance, right? Which is this like UI element prefab, but we're referencing like the compass marker script on it. All right, so we're passing in those two things into register compass element. All right, so if I go to compass, there's a bunch of properties up here. We have some fields, private. And remember, here's a dictionary, which I'm going to have to explain how it's working. And last class, remember, we talked about a list. And previous to that, we talked about an array. And so a dictionary has some benefits. It's a different type of data collection than a list or an array. And they're used a lot. I actually did read ahead, and I noticed that they're kind of not. They're using dictionary in an interesting way, I'll say that. But they're not actually using the dictionary what it's the real like benefit of using it. Anyway, on awake, go out and find me the player character controller. Sure. And then ultimately all it wants to do is saying, hey, for the character controller, go get me its transform. So all it really wanted was the player transform. That's being saved out in this field up here. And then what it's doing, it's saying, hey, give me the width. I want to figure out the width and the height of this compass rectangle, and we're going to use that for placing our little radar dot later. So it's like saying, give me the width and divide it by the visibility angle. So the visibility angle is 180 degrees. So after reading through the script, it became clear to me. So it's like, remember when let me just hide this for a second and just click play again. And remember when you're looking around, you only see stuff that's so the two enemies are right in front of me, so they're like in the middle of the compass rectangle. And if you look up and you look down, it doesn't change the direction from you to them, right? So that's important to note. And as I look away, I'm kind of looking like 90 degrees away from them. They're like on my far right side. It's almost like peripheral vision, right? Like if I keep looking away from them, they're outside my field of view almost. So it's almost like the enemies have to be within 90 degrees. So it's like your field of view is 180 degrees, right? 90 degrees all the way to your right and 90 degrees all the way to your left will be able to paint the enemy on the radar, on the compass. but if they're any farther than that, we don't see them, right? So that's important to note. So our field of view is like 180 degrees, 90 degrees on each direction. So feel free to ask questions because all that is important to begin to understand how this compass is working. So like I'm going to turn my little element back on, and so if it's dead, if the person is dead center to me, let me just make a quick sphere. So basically, if the sphere is like dead center to my field of view, it's going to be like in position x0, right? Dead center of my radar. And if it's way off on the side of my field of view on the left, it's going to be over here, right? So it's like saying the sphere would be like way over here, right? More or less, like over here on my left in my field of view. So, and it's at negative like 190 here. Okay, so and then on the opposite side of this, you know, the right hand side, it's at like 190. So how are they figuring that out? So that's where this like visibility angle, that's why it's like 180 degrees, your full visibility angle. And what it's saying is your width multiplier. So take the width and then divide it by this visibility angle. So if you remember the width, here's 388. This is the rect width and height. So if I bring up my calculator, we're going to do 388 divided by 180, I believe it was. Okay, so it's like saying, however, and it was around like 2.15. So it's like saying, whenever I figure out the angle, you know, that this object is within this 180 degrees arc, I know that I have 388 like pixels or screen positions or screen pixels to move in this kind of these width units. I have like 388 to move from left to right, and that needs to correspond to my field of vision of 180 degrees. So that's why they did that, and so that's like a it's a kind of like going to be like a conversion factor when we deal with the angles, and then we have to figure out where to place it within this rectangle. And the height offset is just give me the height and divide it by 2. So the height was like 30. So it's 30 units from the top to the bottom. And we just need to know like, oh, 15 is like the center spot of it. So that's all these two things are doing. Cool. So register compass element gets called, right? Yeah, so compass element after it initializes the marker, it then says register compass element with my transform, the enemy transform, and that marker instance, that compass marker that was just created. So when that gets called, we basically say, hey, the marker, the prefab, take its transform and set its parent to compass rectangle. Compass rectangle is just the rect transform of this compass here. As if you see it right there. So the compass knows about its rect transform right here. So that's why when we create these prefabs, they get placed underneath here. They get placed underneath the compass because they got its parent has been set right there. All right. And after we set the parent, we use our dictionary, and we're going to add an entry or an element to our dictionary, and it's going to be a key value pair. So when you add a new element to a dictionary, you need to have the key that you can look up the entry, and then the value that it's associated with. So it's a mapping. There's like And the key happens to be the enemy's transform, and the value happens to be the compass marker script. Remember, I was saying before, like, you can set the key and values to whatever you want. You just need to define them first. So here we have the dictionary. So it's like saying, hey, this is going to be coming from system collections generic. It's a generic collection. That's why it's got the angled brackets. So this is the type that we're going to be creating our variable of. Saying it's going to be a dictionary, and that dictionary is going to have keys of transform objects and values of compass marker objects. And we're going to call it, this is the name of it. It's a field, so they do m underscore member variable equals new dictionary, and you just have to state the types again, and then you call it. It's like you're calling like the constructor for this when kind of basically it's creating a new dictionary object that can hold transforms as keys and compass markers as values, and the dictionary is empty at this point. And the real value of the dictionary is that like you can look up the keys instantly. So you kind of have to know when you're adding elements to the dictionary, you need like a handy way to quickly have access to the keys, and then you can look them up in constant time. This developer ended up just looping through the elements in the dictionary, much like an array or a list. So, okay. It has a value in it because they needed to remember both the transform of the enemy and the compass marker that's associated per enemy, and they need them like in a nice organized way. So I can see why they used the dictionary, but then they ended up just looping through it like every update loop, but which is more similar to like an array or something. But interesting. In either case, we added our element, our enemy transform, and the compass marker associated with that enemy to our dictionary. And if that enemy ever gets destroyed, we remove it from the dictionary. So the big next step here is what's happening in our update loop here. And they did say this is very whippy and needs to be reworked. But so what they're doing is doing a for each loop. If you remember, for each loops through every element. So it's like I went through like what a for loop is and a for each loop. And a for loop, you basically set up the iterator, and you have access to each element more specifically. But for each is a very modern way of looping through stuff. You just say, hey, create a variable called element. I mean, the type is var says, hey, compiler, figure it out. But for education purposes, not that good. But if you hover over it, you see that it's of type a dictionary that has this key value pair. So every element will have this key value pair. That's like an element within the dictionary. And in the dictionary, a collection, we're going to loop through each element. So what are we going to do in it? All right, we have some floats that get created. That's good. And now if element, you have to remember the element in the dictionary, which is just a key value pair. So you can say dot key or dot value to get access to it. So the value is, if I hover over it there, you see it's the compass marker. And so this is each compass marker that's created per enemy. And if it's a direction, we're going to do something to it. And this is not a direction. So we're going to come down here. And we're going to do some vector stuff. So I think I found a nice image for each of these vector operations. So we're going to move through this slowly. You did get introduced to some vector concepts, like how to when you add and subtract vectors, you kind of like you go through each component and you add them up or subtract them separately, and then you create a new vector for them. We talked about the dot product, which is really important in understanding how aligned two vectors are. And now we're going to look at some new stuff here. We did kind of talk about normalizing magnitude, but I'm going to cover it now again. So it's like saying, hey, create a vector3 variable called target vector. And we're going to subtract two vectors. Take this position, subtract that position from it, and then normalize it. Okay. Vector subtraction. Very important. So we're going to take the element, the dictionary element, take the key, which, if you remember, that's the enemy's transform. So take the transform that's stored under the key. And then get its position, which is a vector3. It's the world position of the enemy. And then subtract. We figured out, remember, we got the player's transform earlier, and take its position. Now, so vector subtraction is the first thing that we're going to have to look at. Now, to do it arithmetically, it's pretty straightforward. This is a good one here. You just separate out the components and subtract them. Oh, this is a 2D vector. So if A is X is 5 and Y is 4 and B is X is 3 and Y is 1, you just subtract the X's and you subtract the Y's and you get a new vector. So for a 3D vector, you just have a Z. You just take one vector and all its separate components, you subtract the next one, and then you get something. But when you do vector subtraction geometrically, it actually means something. So say that this is the A vector, right? And we're subtracting B, or negative B. This is the difference. So we're looking at the difference between the two vectors, which actually is like the direction. It's like the distance and the direction you need to go from B to A. So it's better to, the best one I saw in here that was kind of actually, you could take any of them. So this one's fine. So imagine this is world space 0, right? This is the dead center of our world. Now, imagine that the enemy, I think they're subtracting, the enemy minus the player. So imagine that A is the enemy. Like, this is the number of units you need to go to place the enemy, right? In this hypothetical. So it looks like the enemy, this is 2D space, but like a lot of Y, a lot of positive Y, and a little bit of negative X, right? And this is where the enemy would be on our 2D game map. And then if we place the player, it looks like a lot of positive X and quite a bit of positive Y, just not as much Y as where we place the enemy. And so these are the enemy's position and the player's position, say at game start. And this is like the dead center of our world. Now, if you take A minus B, you take the A vector, the position. So a vector3 position means what is the distance from world space 0 that this element is placed, its position. So this is the enemy's position. the player's position from world space 0. Now A minus B, take all the components of A, subtract B from it. What you really get is the direction that you need to go from the player to the enemy. So it's interesting that B is like the starting point of our journey to get to A. So this is really useful in saying, hey, where is the player at this moment in the game world, and where is this enemy? And what is the direction that the player must go to reach the enemy? So it's not only the distance that they need to go, but it's like the precise directions. You need to go a lot of negative X, and you need to go a little bit of positive Y for the player to reach the enemy. The vector difference between the player's position and the enemy's position. So this is really important. It's weird that vector subtraction is, in this situation, like when we use it, it's like vector subtraction is more important than vector addition. All right. So the arithmetic rules are pretty straightforward. Just take the subtraction of the elements. But in the geometric interpretation, is it gives you the direction that you need to go from B to A. So it's really important to understand, because we're using it right now to be like, wait, what is the relative orientation between the player game object and the enemy game object? So definitely let me know if you need me to repeat anything, because this is kind of I know this is the hard, all this vector stuff and geometric stuff is hardest to understand, especially when it gets moved up into 3D. But it's used all over the place in gaming. So target direction is the enemy's position minus the player's position. And notice they normalize it. So after we figured out what is the actual direction you need to go to get from the player to the enemy, they normalize it. So this vector has a length of 10 units. And when you normalize it, we get the same direction, but we get a vector that's parallel to it, has the same direction, but it's a length of 1. All right. So this is like saying, hey, to go from the player's perspective, right? The player thinks they're at the whole world revolves around them. So we're at world space 0 in the local space of the player. And they think, hey, I got to go in this direction to get to the enemy, right? But the enemy is kind of far away. And right now, I don't need to know how far away the enemy is. I just need to know the general direction in a nice unit-sized vector scale of 1. So more like the normals. We need to know the pointing direction. We don't care how far the enemy is. We just need to know the direction to get to the enemy. So vector A, whatever the big length is, when we normalize it, we turn it into a unit vector, just a length of 1. All right. So at first we said, okay, now we know the direction and how far the enemy is. But we don't need to know how far right now. We just need to know the direction. We need a unit vector. Something's going to happen where we need a unit vector. That's why they normalized it. And normals, unit vector. And then they say, okay, now we're going to take what we just normalized and project it on a plane, and the plane's normal happens to be pointing up. So when you project onto a plane, you need to pass in the vector 3 that you want to project onto the plane. And then you have to specify, well, how is this plane oriented? Is it facing up? Is it facing down? Is it facing left, right, whatever? This one happens to be facing up. Okay, project on plane. So the best image I found for this is this one, because the plane here is actually pointing up. It's a floor plane. So this plane, its normal is pointing dead straight up, 0, 1, 0. And that means the plane is sitting on the floor. It's sitting flat looking up. So to project on a plane, we have a vector, a 3D vector, and we project it. We basically say, what is this vector if it gets projected onto this plane? This plane happens to be like sitting on the floor looking up. So what happens when we project a 3D vector onto a plane that's sitting on the floor is we get rid of the y component. We just keep the x and the z. We like flatten it out. We're like, okay, we don't care about height differentials. I don't want to do that. That's complicating my math. I just want this vector to be sitting on a floor plane, flat. I just want to know the x and y direction. But when you project on the plane, it keeps the unit scale. So now we're like keeping our x and y components, but they've been adjusted because now y is 0. Like we're not pointing anywhere up or down. We're just pointing left, right, forward, backward. But we've kept that size of the vector, which happens to be normalized. You could have normalized it afterward, but in their steps of operation, we're like, tell me where I got to point toward the enemy, A minus B, and then resize that vector to unit size, and then project it on a plane. Basically, kill the y, but still keep it unit sized. So now we know like how to point toward the enemy, from the player to the enemy with a unit-sized vector that does not regard itself in the y, up or down. We don't remember when I was looking up or down, it's not impacting the compass. That's why we only care about how in front or to the side the enemy is. All right, next, player forward. So project onto plane. Take the player, the local forward of the player, wherever the player is rotated towards, give me the local forward direction in world space. Okay, returns a normalized vector representing the blue axis, basically saying wherever the user is locally looking forward, tell me it in world space. And then project it on a plane, even if you're looking up. So it's like, even if I'm looking up, I don't care about that information. Project it onto a plane. Just tell me how much they're looking to the left and right in a unit-sized vector. And that's what that's giving us. So after we know the relationship of the player to the enemy in just kind of like x and z, and now we know where the player is looking, only in the x and z, then we can figure out the angle between the two vectors. The angle being 0 to 360 degrees, because now we got these two nice little unit-sized vectors. One pointing at from the player to the enemy, and one pointing where the player is looking. And there's some type of difference. Like you're not always looking directly at the enemy. So if I click play, we happen to know that the enemy is like out in front of us right now. That means the angle difference between the two of them is 0. Even if I'm looking up or down, the angle difference is 0 because I'm looking directly at where the enemy is. And even if I start to look off, this might be like -5, -10, -15, -20. and then +5, +10, +15. You know, it's just like a unit circle. So that's how we can start to get the angle between the two vectors. And so that's player forward and target direction. And then there needs to be an axis. So since that's why they like cooked everything down based on projected the onto plane, a plane that's like sitting on the floor because we got rid of the Y. And so that's the axis, right? And so we need to specify that same axis when we want to measure the distance between, or the angle difference between these two vectors. And so we get the angle here, right? All right, that was a lot of work and some complicated vector mathematic ideas, but ultimately we cooked it down to a 0-360 angle. And I guess that means assigned angle. I guess that means not 0-360. I think that means like -180 to 180. Like negative meaning to the left and positive to the right. I'm not sure. I'd have to do print statements. Someone guessed there. But when I look down here, I'm actually no, I know it is because I'll explain that part next. Okay, so direction vector. So we're going to take the key, which is the enemy transform, and we're going to take its position, and then we're going to subtract the player's position, which we already did. So it's a little bit of sloppy. Like if we already calculated this, we shouldn't calculate again, but whatever. So we have the direction vector, right? So height difference equals, so remember that now there is a y component because we didn't cook it out with project on plane. And this hasn't been normalized either. This is like the raw vector, like however big it is. So whatever the y difference is. So when I'm looking at the, this is the difference from the player. The enemy subtracts the player. So this is the difference from the player to the enemy. So the player is at y of like -0.2. And the hoverbot is at 0.5. But they're basically like on the same level. We're on the same level here. At the turn, you have to go downhill to get the turn. So the enemy turns at negative like 7.7. So there's going to be a bigger y difference. So here there's going to be a small y part of the vector for the hoverbot and a much larger negative one for the turret. Okay, so the height difference multiplier, he just put a 0.2 in. Okay, so whatever it is, just multiply it by 2. They figured out that makes sense. But then we're going to clamp it. So we're going to pass in this height difference, which was the y value, difference between the enemy and the player, and multiplied by 2. And then remember there's a min and a max. So we take the height, the rectangle height, I think it was like 30. Yeah, 30. So you take -30 divided by 2, or 15, and multiply it by the margin ratio, 0.8. So it's like it's just kind of shrinking it a little bit. It's kind of like meaning it wants to leave margins. We don't want to put stuff on the extreme edges of our compass. Like only put stuff within 80% of the farthest point is basically what that means. And then the same for the top. So we're clamping it. So whatever this value comes out to be, we're going to clamp it between these two values. If it gets too big, I don't want it to go outside the bounds of the compass height, basically. And it was 2, right? Yeah. Okay. So, for example, the player to the the player to the hoverbot, remember I said it's got a very small y component, and they're just multiplying it by 2. So the enemy hoverbot's this little compass element, it would always be something small, like, I mean, I think it was like 0.5 or something, and then times 2, maybe it's like 1, but see how like just moved up on the bar just like a little bit. So the enemy hoverbot would be somewhere around here, and the turret has got -8 units, and what was it was times 2, -8 times 2, around -16. So you can adjust that multiplier, but they did that because that's felt good. Like -16 is somewhere around here, which kind of gets too far. So it'd be clamped. So it'd be clamped somewhere around here. So anyway, that's why the enemy turrets appeared at this bottom part here. So that's how the height is being determined. And we're getting closer toward the end. So distance ratio. Okay, so take this directional vector that we just found, how do we point from the player to the enemy. Now take the magnitude of it. So the magnitude is just how big the vector is. So like a unit scale vector is a size of 1. And the magnitude is just like the distance. This is like how far would I have to walk to cross this whole vector, right? So that's what the magnitude is. It's like the distance. So it's like saying how far is the distance from the player to the enemy, and we divide it by the distance min scale, 50 units. Okay, so everything's in meters. So this has been divided by 50 for whatever reason, and then we clamp it. So this is a different type of clamp. This is clamp 01. This means we clamp the value from 0 to 1. So I'm guessing the distance is on this board. Let me take a look here. So the player's over here around -28. And it's -7 on the Z. And the enemy hoverbot here is 6 units. So maybe about 20 or 30 units. You can also see these bigger squares here are 10 meters. So you can say if the player's around here, we have 10, 20, 30 meters to here or so, and 40, 50. And then so it looks like maybe it's like 100 units out to the turret or so. Looks like it's about 70 or 80. Yeah, okay. Okay, so it divides by 50, and then you have to clamp it. So that means we're going to be clamped between 0 and 1, which is a common range that we deal with. So sure, so the turret, so something like the hoverbot, it might be like a 0.7 or something, and the turret is definitely past 1. It's more than 50 units, 50 meters out. Based on what I was just seeing, it's probably around a 2 or something, so it'll be clamped off at a 1. All right, we'll try to figure out why they want to do that. But here's a big part. So the angle between where we're looking and the direction to the enemy, right? If it's greater than negative visibility angle is 180. So -180 divided by 2, -90. That's why I said the signed angle is definitely negative to the left and positive to the right. So if the angle is greater than -90, and if the angle is less than 90, so if it's within this range from, you have to remember, greater than -90 means it would be shrinking. So -90, -80, -70, -60 means it's, rotated to the left 90 degrees, but as it's going -80, -70, we're getting closer to zero, meaning pointing directly north, but directly forward. We're looking at whatever it is. So this means that if we're greater than -90 and less than 90, if we're within this acceptable viewing range in our peripheral vision, basically, then we're going to do some stuff. If we're not, meaning this thing is like behind us or too far to the left of us, just turn its alpha to 0, meaning make it invisible, the little circle dot. But if it is within viewing range, make its alpha 1, make it opaque, invisible, and take the local position and set it equal. Now you have to remember this transform local position is just the x and the y here. This x and y. So it's a new vector 2. So even though there is like 3 components here, the z, this is a rect transform, and it pulls in an x and a y. So new vector 2. Now here we have, take the width multiplier times the angle, right? So the width multiplier was, okay, take the width, like 388 divided by 180, it was like 2.15 or something. So take this 2.15 and multiply it by the angle. So this is the x component, right? So that means if it's dead center, then the x will be 0. Now let's just say it's like negative, for argument, let's just say it's like -10 units, meaning it's a little bit to the left. So that would be 2.15 times 2.15 times, good stuff, this calculator. 2.15 times -10. Oops. 2.15 times -10. All right. Okay. No, it was, the negative was messing up. So here we have -21.5, right? And that's the position it would be. And so if it's something more extreme, like -90, it's way off, just on the verge of our vision, times 2.15, it'll be -193.5, our way to the left. And then the same on the right side. So that's how we're calculating our left and right, our x value. Okay, and so that was just taking in the angle. And then we have the height difference here, which is take that amount of y. And then remember, it was doing this clamping thing here. So take the height difference for basically the hoverbot would be like almost 0 or something, but the turret was something like -8 units. -8 times this multiplier of 2, -16, and then clamp it between, it was like 30, it was like 15 and like 0.8, right? So like a little margin in there. So 15 times 0.8 or something like around like -12 to 12. So we kind of, the big turn would have pushed off, would have been too far, and so it would have been clamped to like -15. So I'll just put that in just so you can see that. It would be somewhere down around the bottom of the bar like this. All right. So that's how we're getting the local position here. That's how we figured out, from all this, we figured out the X and the Y for placing it on our compass. And then the scale. How big should we make this thing? Okay, so scale is a vector 3. So it looks like we have vector 3.1, which is just 111, and then multiply it. It's interesting they're using alert for this. Usually use alert for like the animations, but they're lerping. So we have our A and B. 1 to min scale, which is 0.5. Okay, so our acceptable value range will be 1 to 0.5. And then our t value to determine where we are between 1 to 0.5 is this thing here. And that's why it's clamped from 0 to 1, because our journey, when we lerp, we say, okay, we can journey from A to B, and t is like where we are in our journey, the amount of time. Like if we're at 0, it means we're at the beginning of our journey. So we're at A. And if we're at 1, we're at the end of our journey. And so we're at B, and you can have anything in between. And so distance ratio is the magnitude divided by 50. So, okay. For something like the turret, where this will be past 1, so it clamps to 1. And so we're going to get our full effect here. Which seems to be 0.5. So if you're really far away, you're going to be shrunk down to 0.5. And something like the hoverbot is closer. I said it was something like maybe like 0.7. So we're in our journey. 0.7 means we're getting closer to min scale than to 1. So we actually have, maybe we're like around 0.6 or 0.7 or something. So anyway, that's how that scaling is figured out. And the scaling is here. So I just make it 0.1 just to like show you how it can be. I can't even see it at that. So I'll make it 0.4. All right, and that's what it looks like when it's really far away. So that's a lot. You know, this is like a complicated concept, how to like boil down 3D distances and directions and angles into like a 2D HUD element. But there you go. And if you watch the compass at the top, you can see how it's updating based on all of this 3D information. Cool. So let me know if you have any questions. And those were 3 scripts that we went over. So let me just recap that. So on any of the enemies, there is a compass element script, and it is pointing at a prefab compass marker enemy. And on that prefab, it is a UI element, the rect transform, but it has this compass marker script on it. And we went over that script. And then that all pointed to underneath the HUD, there was a compass. And here's the compass script. And that's the 3 we covered today. The compass element, the compass marker, and the compass. And it had a lot of vector ideas in there. So we covered vector normalization, vector magnitudes, vector subtraction to find the direction from one position to another, and projecting on a plane to get rid of the 3D component and make it a 2D vector. Cool. Let me know if you have any questions.